Okay, the first thing is some students say like we need one more quiz. It is not the case. Okay, if you check the syllabus, okay, the syllabus clearly says like we have 5 quizzes and we take the highest 4 quizzes scores for the final grade. It's let me show you. Maybe how do I? Yeah, let's. Okay. So this is the syllabus, right? For this semester. Okay. So you see quizzes. Okay. Okay. It's 40%. Okay, 5 quizzes, and the lowest score will be dropped. Okay, so we already have 5 quizzes. Okay, so we don't have one more quiz. Okay, just want you to know. I mean, next week we will have final exam. Final exam is not a quiz. Okay, just like a midterm, final exam accounts for 30%. Okay, according to the syllabus. Okay, so this is first thing I would like you guys to know. Okay. And then the second thing is that there will be like an event that I need to host. Okay, I don't know I should say use chair or host. I mean, 就是那个耶诞节那个小孩来报佳音，那他们今天早上会来系上。Okay, they are, I mean those like kids, those kids are coming to our department to send us like a Christmas blessing. Okay, so as a department chair, I need to go down and just accept their blessing. So it shouldn't take long. It should be like 20 minutes at most. Okay, so just for you to know. Okay, it will interrupt our class a little bit. Okay, so but I'm sorry for that. But yeah, I mean, what can I say? Yeah, so that's okay, and then let's yeah. So we have like the last it's not working. The extended desktop is really a stupid design. 等一下，我这个，对啊，要把它移过去。有了。OK。Okay. So finally, we finished the third section, right? Diagonalization and we talk a little bit about the fourth section, Hermitian matrices, right? Okay, so my estimate is that, okay, we would be able to finish the section 4 and the section 5 for this chapter, but probably not the whole chapter because this chapter has a lot of material. But to be honest with you, like the Hermitian matrices and the stuff that we are going to talk about, okay, has a lot of to do with like if you are into deep learning, the foundation of deep learning, okay, you can talk to like some PhD students who are really into like the theory in deep learning, okay. So this type of stuff like really helps, okay. And we talk about, did we talk about this? Or we just finished like the last section? 我们是讲到哪边？不好意思，有点忘记。你们来的都是上个礼拜没来的，你们在轮班吗？啊？哪一页？这边这个都讲过了嘛？这个讲过啊。第三章。哪一章？啊，这一章还没讲完吗？哦，这个，这个例子还没讲完 ，sorry。We finished this one, right? Oh, not this one. We finished this one, right? Okay. And this example, well, to be very honest, I think we finished like hand wave this example because like you guys can do the computation yourself, okay? 对不对？是不是在这边停下来？对不对 ？Okay, good. Okay, so as I said, like I will try to finish this section and next two sections today, hopefully. I mean, if that's about it for the final exam. Okay, and the final exam will cover everything from the beginning to whatever we finished today. But of course, like more percentage will be given to new material because we have the midterm, right? We already have the midterm. So roughly 20% to 30% will be dedicated to the material covered by the midterm. And the rest will be dedicated to the new material, okay? Some of the stuff is not that easy to divide. You know what I mean? I mean, mathematics is just like you build on the previous material to continue like what we are. The new one. So roughly 30% for old material, 70% for new material. But it's roughly this much. Okay. So, back to the material, okay, the new material. So, n times n matrix A has fewer than n linearly dependent eigenvectors. We say A is defective. Oh yeah, I think we finished this slide as well, right? I mean, I just told you like you can do the computation of this. You can compute the eigenvectors and see like it does not have like these two matrices do not have like three independent eigenvectors. Okay, if I remember, like they are, I mean, each of them has like two different eigenvalues. I mean, one of them is like a double solution. Okay, 重根, and then what I mean. For each one, you can only derive like one eigenvector. So that's the issue. Okay. So this type of like matrices are called defective. Okay, defective. And then, okay, the next thing is a little bit more interesting. Okay. Because we already know, like, if a matrix is diagonalizable, okay, then it can be represented by this one, right? D equal to x, inverse AX, right? Or put it another way, the original matrix A can be written as XD times X inverse, right? Right? I mean, they are equivalent, right? Okay. So if Px, okay, if we have a polynomial like this, Px equal to am xn to the power of n plus an minus 1 to x times x to the power of n minus 1 and so on to plus a0. Okay, it's an n degree polynomial. And a is, we already given the a. So we can compute this one. How do we compute this? P of A equal to this one. So how do we compute this one? Okay. Oops, sorry. Okay. The idea is like this. Okay, because we can represent A as x dx inverse. So we put A as x dx inverse into this polynomial. Okay. Your x to the power of n will become like this. Because like each your x dx inverse to the power of whatever, okay? I mean, for example, square equal to x dx inverse, x dx inverse, right? So these two terms cancel out each other, becomes I. So it will become x d squared x inverse, right? Right? So because of that, okay, okay, I mean, each of the xn becomes x d to the power of n, x inverse, okay, and so on. This is d to the power of n minus 1, x inverse, and so on. So, I mean, each term will have x in the front, x inverse at the back. So you can put x, here, put the x inverse at the back. Well, the last term, I can be written as x times x inverse anyway, right? So you can convert the original formula like this into here. Once you have that, obviously this, according to the definition, is x times polynomial d x inverse, right? Okay, and we know that, I mean, it is relatively easy to compute like a certain power for diagonal matrix, right? Because for example, well, d squared, it's just going to be, for each term, for each original term, they are all zeros. For each original term, you just put a square here, right? Right? So d to the power of n, you just do the same. I mean, nothing changed. Okay. So it's very, very convenient to compute that. So, and then, you know, once you do that, you will find that, okay, you do each of them, and then, you know, you put them together. This thing, if D is like this, then what you are computing, the PD, is actually P, okay, lambda 1, P lambda 2, and so on, P lambda n. All the others are 0. Okay, so it becomes like a, you know, relatively easy to compute. Okay, so in other words, let's go back to P of A. Eventually will become X times this P of lambda 1, P of lambda 2, P of lambda n, 0, 0, times X inverse. Okay, it will become something like this. Your P of A, right? Right? It should be relatively easy to understand. So let's you know, give like an example here. Okay, let's say P of X equal to X squared plus 3X minus 2, and then we want to compute P of A for this matrix. Okay, of course, like for a question like this, I have, if I give you similar question in the final exam, I mean, the size of matrix has to be small. Otherwise, you know, it takes forever to compute. Okay, but the idea is just like okay, first you diagonalize A. So I mean, you compute the eigenvalue and eigenvector for matrix A. You are going to get like the lambda 1, lambda 2 to be 1 and 0. So for lambda, when lambda is 1, you get the eigenvector minus 2, 1. When lambda is 0, you get the eigenvector minus 3, 1. So in other words, okay, A can be, you know, represented as like this. Okay, so you see, this is like the first. I mean, you have two columns. The first column is like the first you know, eigenvector. The second column is the second eigenvector, and this one, okay, is the diagonal matrix. Okay, with like the diagonal terms to be eigenvalues. And of course, it takes you some time to compute this one, but because this is 2 by 2, this one should be relatively easy to compute, right? Okay, you can do the computation, the inverse by yourself. Okay, so once you have this, obviously, okay, you can represent A. I mean, we know we can represent A with this thing, okay. And then, okay, the P of A equal to this one, right? And the X is like this. X inverse is here, okay? And your P of D is this one, right? As I said earlier. And then pretty much you just plug in like, you know, 1 to the polynomial, you get 2, okay? You plug in 0 for the polynomial, you get negative 2. So this is what you have. So it's going to be this one multiply this one multiply this one. I mean, the result is this. Any question? I mean, this obviously apply for like matrix. I mean, with size greater than 2 by 2, right? Yeah, I mean, but in the exam, I mean, to be very honest with you, like, because I need to, I can only, you know, check your concept. So I have to limit, like, the size of matrix to like roughly this size. I mean, for the amount of computation here, it should be reasonable, right? Should be reasonable. Okay. So we also know, okay, I mean, you can use Taylor series, okay, to write e to the power of x as this one, right? Okay, you can expand like you know, e to the power of x like that. I mean, you should have learned this from your calculus class, right? Like the freshman year. I hope you still remember something from there, okay? So because this is obviously also a polynomial, right? So for any n times n matrix A, okay, you can represent e to the power of A as this. Okay? So if A is diagonalizable by x, okay, then we can write, you know, A to be x d x inverse. Then E of A will become x times E of D x inverse. So if D is like this, where like diagonal terms are the eigenvalue of like the matrix A, then okay, E of D is going to be this one. And pretty much like E of A will be just like x times this one times x inverse. Okay. So you can also compute the exponentials of matrices. Okay. Once you are able to compute the polynomial of matrices, okay, because exponential, I mean, exponent, I mean, the e of power of x can be represented as polynomial. So that's it. So again, I mean, we use the example, like 2x2 example. Okay, so is this the same -2, 1, 6, 3? Yeah, this is exactly same matrix A. So we know like we have two eigenvalue, 1 and 0, and their corresponding eigenvectors. So we can write as like this. And the E of A, it will be x times E of D x inverse. It will be this one times this one times this one. So the result will be this. So far, so good? Okay. And then, okay, there's also one important application of this type of stuff, okay? It's called Markov chain, okay? Markov chain is used to describe a stochastic process. Okay, I mean, if you have trouble with like this term stochastic, okay, just try to translate this term as probabilistic. Okay, probabilistic, because like you guys, are you guys taking like 机率统计 right？这个学期对不对？机率统计，你们在修机率统计嘛 ？Okay, so the stochastic is another way to say probabilistic, or 就是随机的。So it's a probabilistic 随机的 process. Is any sequence of experiments for which the outcome at any stage depends on chances. Okay, a Markov process is a stochastic process with the following properties. First, the set of possible outcomes or states is finite. Okay, here we usually consider the states. Okay, and then the probability of next outcome or next state depend only on the previous state, and the probabilities are constant over time. Okay, so we can understand like if you are given the current situation, and you are given like current state. Let me put it this way: current state. Okay, and you are given this like a transition probability already. Then you can compute the distribution, probability distribution of the next time step. Okay， 我举个例子来讲，就像说，你现在就说这个，现在假设你现在有的这个，用什么东西当例子比较好 ？OK， 假设，这个是。这好像也没有，没关系，我记得等一下就有例子了。对，等一下我们就用这个例子好了。Blue-green color blindness，OK， 这个是那个色盲，蓝色色盲跟绿色色盲 ，OK， 这个等一下我拿这个来当例子好了 ，OK。那我们先讲一个 definition。A vector is called a probability vector if the entries。The sum of the entries, okay, is 1, and each component is non-negative, okay， 它们就大于等于0，然后加起来是1 ，OK。那这边我们这个就是那个有讨论到一个东西，就是说你那个这个就是一个很典型的所谓的 Markov process。就是说，你看哦，我们现在讲说这个就是说蓝色的跟绿色的色盲，就是说假设 ，OK， 你这个，你看哦，上面这个1，下面这个0哦，代表的是你的 time step， 就是1代表下一个 time step， 0代表这个 time step，OK。然后这个 x1 x2 代表的是说，你如果说是，譬如说你前面一代，因为这个是色盲嘛，你是一个 generation 下去看的，对不对？就是你这一代色盲，下一代是不是会是色盲？所以那个 x2， 我们假设x1 代表是 blue 好了，蓝色色盲 ，x2 代表是绿色色盲。所以，如果说你这一代是绿色色盲，你下一代就是蓝色色盲。它的意思，这个事实的意思是这个意思。OK， 那你这一代是应该这样反过来讲，你这一代是蓝色绿色色盲，你前一代一定是蓝色色盲过来的。那你这一代如果说是绿色色盲。So if you are green color blindness, okay, green color blind, then you either there's a have 50% probability your previous generation is like a blue blindness, or 50% your previous generation is like a green blindness, green color blind. So if you can, because this is like 这个看起来是线性的嘛 ，so you can represent this one by this, right? And 如果说你看清楚，你就会发觉说，这个的 row matrix 这边的 row matrix 加起来。row matrix 一定是所谓的 probability vectors， 对不对？0加1等于1嘛，1/2加1/2数等于1。 这没问题。OK， 因为你几率和要是1嘛，对。那在这个例子 ，in this example， OK，we have two states. We have two states, blue color blind and green color blind, represented by x1 and x2. Okay? And the transition matrix is this one. For this transition matrix, you can, whatever your current situation is, your current situation, if you multiply the transition matrix with your current situation, you get the next step distribution, probability distribution for different states. Okay? So, because this is A, right? So we just like, we can do the matrix diagonalization, okay? To get like this one. I mean, basically, like it tells us that there are two eigenvectors, eigenvalues, 1 and then negative 1/2, and its corresponding eigenvector are 1, 1 and the negative 2, 1. Okay, so and this is the inverse of this one is here. Okay, so you may wonder, why do we need to compute the eigen? Why do we need to do like diagonalization here? Okay, because think about this. Okay, if you want to see the in the long distant future. Okay, 在很久以后。What is the stable state？ 就是说它最终的时候，它的几率分布应该要怎样 ？Then, actually you are doing this, right? So, according to the matrix, computation, this one, x to the power of n equal to anx to the power of 0, right? We know that, right? And then we know a to the power of n. If we diagonalize a, it becomes this, right? And then it becomes like this one, x times d to the power of n, x inverse, right? And d to the power of n, well, when n goes to infinite. 这个是1嘛，1 to the power n 是留着1，这个是1/2负1/2的 n 跑到无穷大，这样变多少？0嘛，对不对？所以变这个乘上这1000乘上这个 ，OK， 然后再乘上你的起始的状态，然后起始状态是我们给定的嘛，有给定嘛？其实没有给定，但是没有关系 ，OK， 那就可以把它表示成这样子。对不对？没有给定就用 x1 x2 来表示嘛，就这样子。所以就是这边可以告诉你说，我们可以利用那个就是 diagonalization matrix diagonalization 来去计算，就是说在一个那个stochastic process。OK， 就是 Markov chain stochastic process 里面，就是说它最后面的所谓的 stable state。What is the stable state of like a Markov chain? Okay. Of course, again, because it involve like quite a few computations. So in the exam, I probably can only give you 2x2 examples. Okay, in other words, 2 states. But this idea certainly applies to n states, okay? And we use this, to analyze many different things in research, okay? So this technique is useful in in research papers, Okay. So if a Markov chain with n by n transition matrix A converge to a steady state vector X, then X is a probability vector. So first, I mean, you can add this together to verify that. I mean, it must be like a, you know, a probability vector. Okay, and then lambda 1 equal to 1 is eigenvalue of A, and X is an eigenvector belonging to lambda 1. What does that mean? Okay, if it converge, you must have eigenvalue 1. You must have eigenvalue 1. Okay, if you don't have eigenvalue 1, think about this. Then either your eigenvalue is greater than 1 or small or you know, lower than 1, right? Okay, if it's greater than, I probably should use like the absolute value. Okay, if absolute value of your eigenvalue is greater than 1, then that eigenvalue to a power of n, what happens? When n goes to infinite, it diverges, right? It's going to diverge. Okay, and another situation is like if your eigenvalue, the absolute value, is smaller than 1. Okay, what's going to happen is that, you know, then all this eigenvalue, if all your eigenvalues are smaller than the absolute value is smaller than 1, then everything will vanish, right? Everything will vanish, become 0. Okay, which is also not likely the case, right? Okay, so in other words, okay, if you have a steady state, if you have the steady state, then your transition matrix must have an eigenvalue 1 and only 1, 1. Okay, so that lambda 1 equal to 1 is the eigenvalue of A, and the X is the eigenvector belonging to lambda 1. Okay, so you see, let's come back. What is the corresponding let me see. Let me see. No, never mind. Yeah. So the next one. If lambda 1 equal to 1 is we call this dominant eigenvalue of a stochastic matrix A, then the Markov chain with transition A will converge to a steady state vector. So this is like exactly what we just talked about. Okay, so an eigenvalue lambda of a matrix A is called a dominant eigenvalue if its absolute value, okay, all the other eigenvalue, okay, their absolute value is smaller than the absolute value of lambda. For all other eigenvalues, lambda prime of A. So that's it for this section. So we are done for this one. So let's take 10 minutes break. When we come back, we will continue, okay, to the next section, Hermitian matrices. Okay.